those of you that don't know me, my name is Dave Messenger. I'm the director of the center. Very happy today to welcome Dr. Flora Paganelli to join us today to talk about her research. Dr. Paganelli holds a PhD in remote sensing and geophysics from the University of Alberta in Canada and a Master of Science in Geological Survey from the Institute for Aerospace Survey and Earth Sciences in the Netherlands. She's currently a researcher at the SETI Institute focusing on characterization of Titan surface using analysis of the SAR system on the Cassini satellite. So welcome and thank you for joining us.
Thank you, David, and thank you everyone that kind of entertained me this morning. I had some really interesting discussion and also meeting the students during lunchtime. It was a very interesting morning and afternoon, so thank you. Okay, as David mentioned, essentially I've been involved with the Cassini radar team since I believe 2004, and the whole span of the Cassini mission itself has been essentially running and involving people for the past 30 years, from 1997 to 2017. So just ended, as you might know, with the plunge into Saturn last September. And so since then, anyway, and since our last flyby that was essentially in September last year, we've been kind of wrapping up on science and trying to, make some sense of what we have still a lot of work to do. So some of this work is actually kind of a review of what have been the steps throughout the years, mainly work that I've been collaborating with or I've been conducted personally. And so I kind of try to kind of tag a specific paper or something in there just as a record for myself as well. So, and I don't know what is the format here, but kind of go first with the presentation and then questions. Okay. So, brief outline here. Essentially, Cassini radar is essentially a Titan radar mapper that has been configured to operate in several modes. And I will be going through some of the SAR mode configuration and what are the implications of incidence angle and resolution for the interpretation across the swath. So the SAR is per se actually our highest SAR imaging system. We also got high SAR data at higher altitude, but I'm not going to cover those here, so I just mainly focus on the SAR. And high resolution radiometry, which in this context, essentially, we had also low resolution radiometry with multipolarization scans. However, this particular high resolution radiometry mode is actually something that is being acquired during the SAR acquisition time. So the importance of that is the time and spatial correlation, essentially, that ties the two data sets. And I've been mainly focused on that aspect, essentially, for some time, and so some of my colleagues. So we haven't found yet all kind of an agreement to that, but so some example on the use. When I met most of you this morning, seems to have a fairly good background in image processing, and so nothing of the technique, I suppose, that have been applied here should be anything new. And principal component, very standard type of image processing application that can be used, of course, for optical and various wavelengths, name it. And I initially used it quite extensively in with SAR images when I did my PhD with the RADARSAT, because at the time it was actually the only system that would provide multiple mode data acquisition with multiple incidence angle. So I kind of tried to apply that type of process technique to some of our SWAT. SAR-derived DM, which are actually using essentially the stereo mode overlapping high cross-angle intersection of the flyby that we acquired. SAR topo that never been really in the plan as a data product to be there, but it seems that during the mission, one of our bright engineers end up actually finding a way to use a, at the time, kind of odd configuration of the antenna and the beam overlap within the antenna as a way to extract radar altimetry using that he calls SAR topo. So we have streams of topographic height along the various flyby that are actually using this particular configuration. Research outlook and questions. There are still a lot of questions out there. And then some current work related to planetary data system and planetary science informatics, data analytics that is also trying to combine and I guess fill the divide between the planetary science and astronomy community in a way. Okay, so as you can see here, and as I mentioned earlier, there are various configurations that have been applied during the radar acquisition. That goes from radiometry only, so scanning raster that were actually a very high range and very large footprint, but in both polarization, that we had the scatterometry as well, kind of in a raster scan mode, operational mode, with one polarization. And then we had the combination of the high resolution type of data that were actually mainly acquired during the Titan encounter with you know, a variability actually between when you have a flyby, of course you have to account for the variability in range to the target. And so here our flyby will go from from inbound to close approach to outbound. And that means that you actually change range while you are sweeping over your target. And that means that you change incidence angle, resolution, and geometry all together while you are moving along. So the antenna system itself was configured to use is a KU band, and is actually being characterized by 5 beams. So as you can see in the scheme over there, the antenna configuration had the big dish of the antenna was of course used also for communication using a Ka band, and therefore when communication was going, the radar was off. And so throughout the tour, there were specific configuration and orbiting mode that needed to be set priority to the flyby in order to make it work, especially for radar, because it was essentially redirecting the whole spacecraft. So the 5 beam, the center beam, beam 3, is actually a very crucial beam that enabled the calibration of several of the beam 1 and 2 and beam 4 and 5, because the characterization of the, let's say, incidence angle, for example, and footprint within that beam was, you know, established and well defined throughout the flyby. But beam 1, 2, 4, and 5, they were fairly variable because of the spread vertically and horizontally during the flyby, and also because of the overlap. As you can see, the beams are kind of, concentrated really adjacent to each other, but that means that the energy that you are sending and receiving from that footprint is actually overlapping at the overlap of the beams. So you need to kind of resolve. That was actually a good thing for the SAR topo, as I mentioned, because that is a product that turned out to be making a good thing out of a bad thing. Normally, the time of acquisition of the SAR imaging was in the order of 15 minutes or so, and so we were going from 4,000 to 1,000 kilometers at close approach. So it means that at close approach, you had considering the center of Titan, and Titan's radius that we consider as an ellipsoid of 2,575, so approximately 3,000 kilometers. You need to actually consider, and what in some of the slides that will be considered as a close range of 4,000, means that you are at close range 1,000 kilometers of elevation plus the 3,000 of compensated for the Titan radius. So in the altimetry mode is essentially was something that was run at the very beginning or at the very end of the flyby, because essentially as a mode on its own, it was just using simply one beam, and that's why it's actually interpreted in that way. And it was also essentially pretty much at the very beginning, at the inbound for a few minutes. Then all the flyby was run in a SAR mode, and along with the radiometry and acquisition, and then perhaps if there was a chance, there was also another transect of section or of altimetry only. So just as a general idea, and I guess some of you probably already work with radar data, but when working with radar data, we need to actually consider and be very careful with geometry. Now, when we work on Earth observation, our configuration in terms of incidence angle, orbit parameters, and resolution are very much predefined, and during the cycle of our satellites and data acquisition, they are constant. So there is, however, due to the incidence angle variation, depending on Earth system, are between 23 and 55, actually, some of the radar sat. You have the possibility of having different type of, let's say, side effect, which especially in rough terrain, mountainous terrain, will make a big impact on what you see in your derived images. So to start, if you have actually a kind of intermediate incidence angle, you might end up having a possible foreshortening. That means that a sloped terrain that is actually facing the antenna, the radar antenna, will actually be scaled down and shortened in the slant range. And so your image, which is derived from the slant range, you will actually have that slope really looking like a narrow sliver, and while the slope away from facing away from the radar will actually be elongated. Another possible aberration is layover, when actually the foot of a heel will be actually, rather than be imaged in its position in the length range plane, is actually imaged in the back of the top of the heel. So in that case, you will end up having a layover, and so these very bright slope and some flat iron type of configuration that might result from there. When you have a very shallow look angle, then you might end up actually completely overshadowing and shadowing the slope that fades away from the radar. And so having an eye to those effects and how to interpret them in function of the incidence angle and geometry of your data configuration is very important from the processing, but also the interpretation aspect, which is what we were trying to do. So other important element here, as I mentioned, Earth observation is pretty much standard, but when you are actually orbiting a planet, and you, not in a constant orbit, but in just a flyby mode, then your inbound, close approach, and outbound will be really kind of symmetric in configuration. And also your incidence angle, like I said, it could be fairly well calibrated in your beam tree, but on the side it will be variable and and changing. And that is actually what you can see there. This is an example in T3, and you can see actually this is the center of the beam, so closest approach. You have a very kind of mid-level type of medium incidence angle here, but you have quite a spread of going from very narrow incidence angle all the way to wide angle in the inbound and outbound. On the other hand, you have quite an effect also on the range and azimuth resolution of the surface. They are not the same. So that is also, although after processing, those images are redefined to a constant, of course, pixel size, but the data that actually are coming out from the process are essentially characterized by a different resolution. And that, of course, will affect, if you think about it, the capability of, if you have similar features that are present here, here, and here, the capability of connecting them as same feature will be quite challenging depending on the resolution actually present in that specific area. So the challenge has been there, and as you might know as well, when you have, if a feature is, for example, here, you have actually the added deterioration of resolution and incidence angle effect that is completely variable from what you have in the center. So when here on Earth we are actually interpreting data, we are fairly good with kind of a common standard resolution, and we don't have really much variability to worry about. But when we are on flyby mode, there are. Maybe I'm kind of emphasizing too much that aspect, because I'm coming from Earth observation point of view. And for example, when I first started working on the data, I was really concerned about this. But from the planetary aspect point of view and interpretation, I guess there is more allowance for more assumption, and so to kind of put everything in the same basket with a fair assumption. So that is good, but I think it's also good to notice that the reliability or accuracy that you might have here in establishing a feature that might be looking similar to a feature that is here does not come from the same resolution to start with. And so, yes, you need a lot of assumption and dedication and to be trusting what you really map as the same unit or as the same. So that has been done and is all okay, but I just want to emphasize that not everything that is right now in an image with the same, square pixel resolution come from a same effective resolution in the image itself. So here are some of the very first example of what it means actually to have those watt wrap around Titan. And in most cases, actually, we were normally having full flyby, so inbound, close approach, and outbound, the various latitude and longitude, of course, in an equatorial type of flyby or polar. And the polar, actually, one came about towards the end of the prime mission and the first extended mission. But you can see, for example, for TA here, is actually starting with a kind of a close approach and then just have only half of the flyby. That because that was our first flyby, and it's out of sequence it's not called T1 for a reason. So it's not complete because there was a specific need and just an opportunity for radar to actually gather some data. And so when the spacecraft turned, and it was a close approach, so it just is essentially half of a beam of a flyby. And there are several other instances in which actually we end up having some off-shape type of flyby. Here an example as well that shows TA, for example, in T3. So T3 is this one, the full flyby, very well balanced across the equatorial belt, and TA in more on the higher latitude. And you can see actually also the very strange configuration here in the surface and azimuth range resolution between the two. So comparing features that are up here, same as the one up here, is tough luck. And especially when you're trying to make that happen with, resolution. But we did it, and to certain degree of confidence, of course. So as I was saying, here more specific about the length of the flybys and the width. Most of them were in the order of 4,000 to 6,000 kilometers, and the average within the center portion was between 120, 150 to 450 to 500. Now the general nominal pixel size resolution was actually up to under 75.55 meter per pixel. And what else? Oh, another important factor that most of the images were of course collected in the same way in which SAR images are collected here on Earth system, and so using the multi-look technique. And in those, in our flyby, essentially there was as well there a variability within the number of looks. So if you add that as well to the incident angle and resolution, you will have additional effect. Here what, for example, T3 and TA look like. And this is actually our first flyby, was the one that really kind of gave us the wow in terms of alluvial, fluvial feature identification, some later on defined as a possible volcanic flow, cryovolcanic activity flows. We had in this first flyby absolutely no evidence of crater, but then in T3 actually huge crater here, member and SYNLAP appear that were really quite amazing. The range of variability in dB for those images was is normally between -15 and 2. So some of those bright feature here had really, and I would say that TA is probably the one of the few that actually outline such a bright feature. There are very few throughout that actually have comparable characteristics. So we talked with some of you this morning in terms of surface roughness, and again, this is probably old school, and however, the point here is that there is definitely a change in radar cross-section depending on the roughness of the surface and the incidence angle. So here again, when interpreting or trying to establish or characterize the surface variability in those data, you have to make consideration, of course, on your wavelength, that in our case was the 2.17 centimeters, and the various and how that relate to the possible surface characteristics in terms of smoothness factor and incidence angle. So in with all those considerations, some of the let's say characteristics that were fairly apparent actually was definitely the presence of terrain boundary, sometimes linear, sometimes not. So linear morphology were actually fairly visible, especially when the loop direction, here you have a loop direction towards the arrow here, and the flight track is actually going over. So linear features that were actually at a high angle with respect to the loop direction were readily distinguishable. Also very sharp terrain changes along linear boundary. Now, if you see those lines, those are artifacts, so I'm not referring to those. Okay, those are due to the overlap between the beams. Okay. Here we are in, apologize, these images don't look as bright as I thought, but anyway, some of the lake area in the polar region, and there was actually a very, you know, the smoothness and darkness of those lakes really kind of stand out with respect to what we've seen earlier on. So the discovery and imaging actually of such a smooth surface, it was a very amazing find, and that actually evolving a lot of work, especially from the group up in Cornell. They've been working mainly on lake and altimetry data with some of the Italians counterpart from La Sapienza Roma. Some of postdoc actually working there. So in a very simplistic and parametric way, we can consider actually or try to parameterize and derive surface roughness using simple method and empirical theoretical method. So, and as you can see here is essentially all focusing on the or revolving around the incidence angle and the electric constant, the height of the RMS slope, and the wave number that is essentially involved the wavelength and the wavelength itself. So the Cassini radar was essentially a non-polarized and was essentially encompassing all of the sigma naught was actually extracted as a combination of vertically and horizontally polarized return. So, considering the surface reference, some of the first attempt to actually extract the RMS and surface variability were actually derived using this formula and focusing essentially, as I mentioned, only on HH polarization, since the vertical was found negligible. For these 4 different terrain that essentially are expressing footprint of most variable characterization that were identified at the time. So here there is a very dark terrain, a medium terrain, and a bright terrain, U, and a very bright terrain. So they were all fit with a kind of empirical model, and as you can see, actually kind of fairly matching RMS here for the dark terrain of fairly smooth 0.4 centimeter, the medium for 1.12, and at the very bright and bright were actually kind of just off, but with average of 2.5 centimeter. And here you can see actually the variability in the radar cross section. So that was kind of giving at the time. Of course, you need to also establish or make a choice in terms of the electric constant. And here we essentially there were few candidates, and the plot over there were essentially using an electric constant of 2 for hydrocarbon. However, the possibility was also to either use and we definitely identified present through the VIMS instrument of water ice and water ammonia ice. So all these 3 type of candidates are possible, and maybe a mixture of them should be considered. However, for simplistic reason, here are kind of the let's say plot diagram for specific unit that consider the electric constant of 2 for general hydrocarbons. So that really tells you that there is quite a big change in RMS at that small scale on the surface, and with the 2.17 centimeter wavelength, that is a lot. So that means that, for example, for the very bright, very bright terrain, here you are on a surface roughness of 2.5, so which is a centimeter, which is very similar to the wavelength. So all your energy is all reflected back, or there is some other means for which that terrain is so bright, and that is actually something that we think is the case. And I will comment on that later. So when it comes to radiometry data, as I mentioned earlier, the main key component here is essentially the during the SAR pass was the spatially and timely coregister data. And that was really relevant because, as you might imagine, we were also interested with all these, once we start kind of having a sense that there was a dynamic process involving the reshaping Titan surface, whether there was any change. And so having spatially and timely correlated data set that could and be combined the surface reference characteristic, but also with the radiometry, trying to give some insight on the chemical composition to some extent, was important. So in the radiometer itself, actually some nominal characteristics are actually listed here. And again, beam 3 is essentially the key beam that was used also to calibrate the radiometry. And with the total power present, and coming back to the antenna, the antenna temperature actually was combined by a combination of the brightness, average brightness, plus a delta temperature coming from the side lobe effect. So the overlaps of the beams, the remaining beams 1, 2, 4, and 5. So another important aspect of this data set is that the footprint resolution was in the range of 6 kilometers for the beam 3. However, spacing out into the inbound and outbound, that resolution was actually going from 23 to 75. So there was as well a need here to kind of, in order to integrate those data, to actually average down to a common, I would say, footprint. And that was actually decided to be 20 kilometers. But going back to the calibration of the radiometer, so if we consider actually the solid total angle of the antenna pattern, so the antenna temperature is actually characterized by the temperature, brightness, plus the side lobe effect. So the brightness temperature in the footprint define the main beam essentially, and then the TB is the net contribution of the side lobe on the extended source of and the empty space. So if you think about when you have a kind of interference pattern, the further away you are from your target, the lower the effect of the side lobes. But the moment you get closer to the target, actually the higher is the overlap and the side lobe effect. So, and as stated here, a closer approach, actually this effect was in the order, or as much of 30%, so it was really kind of needed to be resolved. And actually, Mike Johnson at JPL is the radiometry expert that has been working essentially on the mission since the beginning, and the one that during the mission, after the mission was launched, there was a Venus gravity assist in order to propel the spacecraft towards Saturn. During that time, actually, there was the possibility to actually have some sun scans, and so define the calibration parameter for the beam 3. And that calibration actually has been then used to actually calibrate the beam 3, and as an average fit, also recalibrate the order being 1, 2, 4, and 5. In addition to that, actually, some data from the VLA system were also used to actually confirm what the calibration results were. And so, all in all, essentially, you know, we can kind of with this kind of approach, we kind of offset the problem of the side lobe overlap. Now, if we look at brightness temperature in terms of physical characteristics, it's actually related to the physical temperature of the surface, and through the emissivity can essentially be expressed as brightness equal to emissivity multiplied by the surface temperature. So through Kirchhoff's law, though, we can reduce the emissivity as a function of reflectivity. So in a simple model, and that is what we consider to start with, we can consider Titan as a Fresnel surface, and so apply this simple model to you know, kind of reconstruct our average result. However, in the real world, there is something else that really has play here, which is volume scattering. Now, volume scattering is actually something really hard to quantify, and especially with all this, the variability in our data set. However, in general, the volume scattering effect is in the order of 20 to 30%, and with the established calibration, we are kind of fairly confident that within an error of 1K of the surface temperature. Now, during the initial flybys, we actually went as a simple model, so we use a Fresnel equation. After Huygens landing, we definitely realized that actually the surface temperature that was actually we were able to derive through, you know, our assumption and characterization was actually quite off. And so after Huygens landed and gave a specific measurement of the surface temperature, I believe it was 33.6, we actually adopted a surface temperature of 94 Kelvin throughout all the data set. And so that is kind of what I tried to kind of summarize over here. And also we had to, in order to compensate that variability and Huygens data, we had to actually really consider that, yes, that there was a need for an additional element, and that was the volume scattering. So if we look at thermal emission, though in a Fresnel kind of environment, and considering still our possible candidate for surface emissivity, this is what we will expect our brightness temperature to behave depending on the different variability in RMS slope in degree. So you can see that if you increase actually your emissivity, you will kind of reduce your brightness temperature quite a bit. The sub range as a you know, as an interval will cover essentially only these portions. So we occasionally we went at these viewing angle, but in very few inbound and outbound portion where, for example, the resolution anyway of the star was like above 2 kilometers or what. So we didn't really get much insight on that. Okay, so moving on. Here, kind of the parameterization that is involved as well, if you consider brightness temperature with perpendicular plane of incidence or parallel plane of incidence. So, and the graph that I just show you is actually characterized using the perpendicular incidence, which is actually what our data have shown. So this portion here was never really fitting our data set. This is a representation of what you see actually in the radiometry data when plotted on the various Titan flyby. So they look very patchy because the footprint and resolution within them is definitely limited with respect to the SAR data, but nonetheless actually very relevant in identify actually surface brightness variability, especially in the dune portion, like in the Shangri-La, Belay, in TA here, Mesoramia, in kind of lacustrine type of environment, and very high volume scattering, very bright terrain here in the Xanadu area. Along with, if you remember, this is the portion where there were like the alluvial fan and the member crater and Sillab that also turned out to be very bright and definitely affected by volume scattering behavior. This is actually the SAR passes, and this is what you can do actually with a little bit of manipulation of the data, I would say. So you kind of get some good, integration. Here I use a 20-kilometer grid, and this was actually very much the standard used throughout for the integration of the radiometry data at high resolution. Some of the characterization or study that were conducted essentially were trying to figure out how to characterize surface terrain based on SAR characteristic and brightness temperature. And as I mentioned earlier, for example, here on Sillab, you can see that actually there are very kind of bright terrains that are also at the edge of the member crater. Some of the fan or alluvium that were present in, this is actually referring to T3. Some hilly terrains. And so this is pretty much kind of a standard type of plotting a region of interest to some extent. And again, various consideration and slight variability could be present if, of course, rather than model for a dielectric constant of 2, you might want to use something higher than that. Other example here for the Adiri Hill, you can see very clearly nice streamline hilly areas along the T8 flyby. Those were actually some mounts surrounded by dunes. Some kind of eroded terrain kind of popping into the dune fields. They were kind of interesting. And actually here is a plot as well, the landing site, the Ogden's landing site that was very much in let's say mixed terrain between the dunes and some dark terrains. As you can see here, actually the dunes were some of the darkest areas in terms of reflectivity-wise for the radar, but also low emissivity from, high emissivity from the aspect of the radiometry data. And they are placed fairly much at the bottom of the scale here. And as you can see, very high brightness temperature. So other plots kind of summarizing the kind of distribution of the first 5 flybys in a wide range of variability. And here we jump into the polar areas and the lakes. So when we actually got this flyby, I think was quite, important to identify, well, characterize brightness temperature as well, trying to have some sort of understanding also through that of what possible composition there might be. So here is actually some cross-section across them, and was really peculiar in this particular flyby was actually the presence of one of the brightest, very bright spot actually in the same flyby that really enables some comparative analysis. So same thing here, use the same approach and a very simplified method as well. And if for the lake area, actually we have high emissivity and brightness temperature, we kind of still consider the model 1, but for the T1, it would definitely not fit, and you can call it actually a cold spot, kind of low emissivity, and definitely a terrain that either for roughness characteristic or volume scattering is definitely fitting more a model 2 type of environment. Here is kind of summarized in a diagram the characterization of radar cross-section versus brightness temperature. And brightness temperature versus incidence angle, and similar to the RMS that I showed earlier. And incidence angle versus, the other one was brightness temperature versus incidence angle, and sigma naught versus incidence angle. So you can see that the bright spot is kind of an outlier here, although being also in a kind of a medium-high incidence angle, which is definitely anomalous. Okay, moving to principal component. So principal component here, you can see that these some of the examples that are following from here are just focusing on T41 and T43. And T21 is a flyby that we actually got in September 2017. So I put it here, but in some of the, I have included in some of the slides and a few at the end. Some work is still in progress here. So anyway, the important part is, okay, we're trying to define principal component to apply a principal component. So first thing here is really trying to match features. And you can see that being actually done pretty much here on these overlapping areas, and If you are not doing that, you end up actually having doubling of feature as this one. However, the very cool part of it, if you can see the result in the principal component, is that this is the incorrect way to do it. When you actually align your images, this is what you get in the PC2. And this is the increase in intensity or variance that you get from a regular image pair to a principal component one. So serious increase in enhancement of feature and also topography that you can outline. Here, more in detail, actually the overlap, and you can see that your features are actually standing up quite a bit, and those data are really great. I mean, as a geologist, I kind of, but anyway, cut it short. This is a simple plot to summarize the eigenvalues from the principal component and how they plot with respect to, the inverse correlation that they show with respect to the incidence angle and the various distribution. Here is the DEM overlap to the principal component 2, and you can see actually a very good correlation between actually what is actually expressed in the PC2 and the DM. The DM was also a secondary product that was provided by USGS and is actually also available in PDS for the science community. This is actually, the noodle here are beam 3 radiometry data that are overlapped on the 43 and 41 flyby. And you can see actually a correlation between actually the low emissivity and high terrain in the radar and the low emissivity in the radiometry, high emissivity in the darker terrain. And these kind of features actually are also in direct correlation with the altimetry data set. So this is something that I'm exploring now. Here is an example of what essentially the SAR topo means. Essentially is fitting the right height through the data, and that fit is actually will turn out to be redistributed or distributing perfectly and matching the power and gain of the data. If you actually use a different height, is actually going to be projected off the data cloud. And this is actually what happened, what I was talking in terms of overlap between 2, 3, and 4, 5. This is actually the linear mask along which actually the SAR topo has been created by Steyer. And the noodle over here, so this is actually a summary mosaic of the principal component 1 from 41, 43, and 21 to 21. And here actually the radiometry data and the SAR topo for the 2 flyby. You can see actually kind of matching feature, especially in the high low emissivity terrain here. Very quickly on the PC2 and okay, so the SAR topo actually used in this type of context was also kind of used to extract kind of structural patterns and trying to fit actually the surface height variability along the SAR track and the SAR topo data. This is actually what is currently the potential inventory of the flybys that overlap to some extent, and that could be potentially used for principal component analysis or other type of technique that will use integrated data set. And there are essentially 3 categories: opposite side, eye angle crossing, and same side. There are all different configurations that will give different results. Currently, I think, like I mentioned earlier, we are still working on the data, and there are still questions that are unanswered and that are still kind of hindering to the clear understanding of how essentially the variability of the data are enabling us to really define or compare geological feature throughout Titan, and our assessment and limitation from there. Now, here's some input for you. I know that some of you might be interested or not in planetary data of some sort at some stage, I don't know, but anyway, here is a link where you might find actually your sources. There are several PDS nodes, and those nodes are actually collecting data from all the various planetary missions. Specifically for Cassini imaging, here's the cartography imaging node, and where you can find the SAR data. Of course, if you are looking into the rings, you have the ring moon system, and for the secondary product like the SAR topo, those are actually all into the small body node. Some information about some of the format that you would expect, and perhaps if you are going to write proposal for data analysis and whatnot, you might want to look into the roadmap study for data product that is at this link, and that was the work that I've been done with other colleagues on for the planetary data system. And to finish, just a link between a planetary data mission and astronomy or Earth-based or space-based observation, telescopic observation. There is really a lot of emphasis from NASA to kind of put this community together and kind of talk in terms of integrated approach for mission planning and Earth observation in order to enhance the science return of the data, and specifically a close approach. One of those will be Lucy, that will actually investigate the Jupiter Trojan, and this is kind of an approach that kind of going to present PSIDA later on in April. And thank you. I'm sorry for being so lengthy, but
we're a little over time. Do we have time for one quick question? Otherwise, we'll just go out for cookies and coffee, and we can talk to Flora out there. Thank you again very much for doing this.
I'm glad you guys landed in such a good place. Yeah, it worked out.